Welcome to lesson 12 in our series of lessons on the application layer for our course Networks and Distributed Systems based on the text Computer Networking, a Top-Down Approach by Jim Caros and Keith Ross. Let's pick up where we left off. At any given time, each peer will have a subset of chunks from the file with different peers having different subsets. Periodically, a user will ask each of the neighboring peers for a list of chunks they have. The user will eventually receive a list from all the neighboring peers. With this knowledge, the peer will issue requests over TCP connections for chunks he or she does not currently have. In deciding which chunks to request, a technique called rarest first is used. The idea is to determine which of the missing chunks are the rarest among the neighbors. That is, which chunks have the fewest repeated copies among the neighbors, and then request those rare chunks first. In this manner, the rarest chunks get more quickly redistributed, aiming to roughly equalize the number of copies of each chunk in the torrent. To determine which request to respond to, BitTorrent uses a clever trading algorithm. The basic idea is that priority is given to the neighbors that are currently supplying data at the highest rate. Specifically, for each neighbor, our peer continually measures the rate at which the bits are being received and determines the 4 peers that are feeding those bits at the highest rate. It then reciprocates by sending chunks to these same 4 peers. Every 10 seconds, our peer recalculates the rates and possibly modifies the set of 4 peers. In BitTorrent lingo, these 4 peers are said to be unchoked. Importantly, every 30 seconds, our peer picks one additional neighbor at random and sends it chunks. In BitTorrent lingo, that new neighbor is said to be optimistically unchoked. Because our neighbor is sending data to the new peer, our host may become one of that neighbor's top 4 loaders, in which case it would start to send data back. If the rate at which that peer sends data to us is high enough, it could then, in turn, become one of our top 4 uploaders. In other words, every 30 seconds, we will randomly choose a new trading partner and initiate trading with that partner. If the 2 peers are satisfied with the trading, they will put each other at the top of their 4 lists and continue trading with each other until one of the peers finds a better partner. The effect is that peers capable of uploading at compatible rates tend to find each other. The random neighbor selection also allows new peers to get chunks so that they can have something to trade. All other neighboring peers besides these 5 peers, 4 top peers and 1 probing peer, are choked. That is, they do not receive any chunks from us. BitTorrent has many interesting mechanisms that we are not discussing here, including pieces or mini chunks, pipelining, random first selection, in-game mode, and anti-snubbing. Here you see a series of transactions between peers to show you this tit-for-tat mechanism. BitTorrent has been very successful, probably in part because of this tit-for-tat mechanism. Now let's begin a discussion of hash tables. The distributed hash table model, circular distributed hash tables, and overlay networks and peer churn. Let's begin our discussion of hash tables. We will begin to examine how to implement a simple database in a peer-to-peer network. This centralized version of a simple database will simply contain key and value pairs. For example, the keys could be social security numbers and the values could be the corresponding people's names, as you see here. We query the database with a key. If there are one or more key value pairs in the database that match the query key, the database returns the corresponding values. So for example, if the database stores Social Security numbers and their corresponding human names, we can query a specific Social Security number and the database returns the name of the person who has that Social Security number. Building such a database is straightforward with a client-server architecture that stores all the key value pairs in one central server. We'll consider how to build a distributed peer-to-peer version of this database instead that will store the key and value pairs over millions of peers. In the peer-to-peer system, each peer will only hold a small subset of the database. We will allow any peer to query the distributed database with a key. The distributed database will then locate the peers that have the corresponding key value pairs and return the key value pairs to the querying peer. Any peer will also be allowed to insert new key value pairs into the database. Such a distributed database is referred to as a distributed hash table, DHT. One naive approach to building a distributed hash table is to randomly scatter the key value pairs across the peers and have each peer maintain a list of IP addresses of all the participating peers. In this design, the querying peer sends its query to all other peers, and the peers containing the key value pairs that match the key can respond with their matching pairs. Such an approach is completely unscalable, of course, as it would require each peer to not only know about all the other peers, possibly millions of them, but even worse, have each query sent to all of those peers. To design a distributed hash table, let's first assign an identifier to each peer, where each identifier is an integer of some fixed size. Let's also require each key to be an integer in the same range. You recall that the example keys described a minute ago, Social Security numbers and content names, are not integers. To create integers out of such keys, we will use a hash function that maps each key, such as the Social Security number, to an integer. A hash function is a many-to-one function for which two different inputs can have the same output, or the same integer, but the likelihood of having that same output is very slim. The hash function is assumed to be available to all peers in the system. From now on, when we refer to the key, we're referring to the hash of the original key. In other words, not the Social Security number, but the integer that has been hashed. So, for example, if the original key is, say, Led Zeppelin IV, the key used in the distributed hash table will be the integer that equals the hash of Led Zeppelin IV. Let's consider the problem of storing the key value pairs in the distributed hash table. The central issue here is defining a rule for assigning keys to peers. Given that each peer has an integer identifier and that each key is also an integer in the same range, a natural approach is to assign each key value pair to the peer whose identifier is closest to the key. For convenience, let's define the closest peer as being the closest successor of the key. To gain some insight here, let's take a look at a specific example. Suppose n equals 4, so that all the peer and key identifiers are in the same range from 0 to 15. That indicates that what we're saying there is that there are 4 bits. All bits turned off is a 0, all bits turned on are 15. Further, suppose that there are 8 peers in the system with identifiers 1, 3, 4, 5, 8, 10, 12, and 15. Finally, let's suppose we want to store the key value pair ID 11 Johnny Woo in one of the 8 pairs. But in which of the 8 pairs? Using our closest convention, since pair 12 is the closest successor for key 11, we therefore store the pair 11 Johnny Woo into pair 12. To complete our definition of closest, if the key is exactly equal to one of the pair identifiers, we store the key value pair in that matching pair. And if the key value is larger than all of the pair identifiers, we use a modulo -2n convention, storing the key value pair in the pair with the smallest identifier. Now suppose a pair, call it P1, wants to insert a key value pair into a distributed hash table. Conceptually, this is straightforward. Pair 1 first determines the pair whose identifier is closest to the key. It then sends a message to that pair, instructing it to store the key value pair. But how does P1 determine the pair closest to the key? If we were to keep track of all pairs in the system, pair IDs and corresponding IP addresses, it could locally determine the closest pair. But such an approach requires each pair to keep track of all other pairs in the distributed hash table, which is completely impractical for a large-scale system with millions of pairs. To address this problem of scale, let's now consider organizing the pairs into a circle. In this circular arrangement, each pair only keeps track of its immediate successor and its immediate predecessor modulo 2n. In this example, n is again 4, and there are the same 8 pairs from the previous example. Now, to continue our discussion, each pair is only aware of its immediate successor and predecessor. For example, pair 5 knows the IP address and identifiers for pairs 8 and 4. But it does not necessarily know anything about any other pairs that may be in the distributed hash table. This circular arrangement of pairs is a special case of an overlay network. In an overlay network, the pairs form an abstract logical network which resides above the underlay computer network consisting of physical links, routers, and hosts. The links in the overlay network are not physical links, but are simply virtual liaisons between pairs of pairs. In the overlay figure of 2.27a, there are 8 pairs and 8 overlay links. An overlay link typically uses many physical links and physical routers in the underlay network. Now suppose that pair 3 wants to determine which pair in the distributed hash table is responsible for key 11. Using the circular overlay, the origin pair, pair 3, creates a message saying who has the key 11, and sends this message clockwise around the circle. When a pair receives such a message, because it knows the identifier of its successor and predecessor, it can determine whether it is responsible for, that is closest to, the key in question or not. If a pair is not responsible for the key, it simply sends the message to its successor. So for example, when pair 4 receives a message asking about key 11, it determines it's not responsible for that key because its successor is closer to the key. So it just passes the message on to pair 5. This process continues until the message arrives at pair 12, who determines that it is the closest pair to key 11. At this point, pair 12 can send a message back to the querying pair, pair 3, indicating that it is responsible for key 11. The circular distributed hash table provides a very elegant solution for reducing the amount of overlay information each pair must manage. In particular, each peer needs only to be aware of two peers, its immediate successor and its immediate predecessor. But this solution introduces yet a new concern. Although each peer is only aware of two neighboring peers, to find the node responsible for the key, in the worst case, all nodes in the distribution hash table will have to forward a message around the circle. Thus, in designing a distributed hash table, there is a trade-off between the number of neighbors each peer has to track and the number of messages that the distributed hash table needs to send to resolve a single query. On one hand, if the peer tracks all the other peers, which could be a mesh overlay, then only one message is sent per query. But each peer has to keep track of all the peers. On the other hand, with a circular distributed hash table, each peer is only aware of two peers. But n divided by 2 messages are sent on average for each query. Fortunately, we can refine our designs of decision hash tables so that the number of neighbors per peer as well as the number of messages per query is kept to an acceptable size. One such refinement is to use a circular overlay as a foundation, but to add shortcuts so that each peer not only keeps track of its immediate successor and predecessor, but also of a relatively small number of shortcut peers scattered about the circle. An example of such a circular distributed hash table with shortcuts is shown in figure 2.27b. Shortcuts are used to expedite the routing of query messages. Specifically, when a peer receives a message that is querying for a key, it forwards the message to the neighbor, successor neighbor, or one of the shortcut neighbors, which is the closest to the key. Therefore, in figure 2.27b, when peer number 4 receives a message asking about 11, it determines the closest key among its neighbors is the shortcut neighbor 10, and then forwards the message directly to peer 10. Clearly, shortcuts can significantly reduce the number of messages used to process a query. Let's watch this query. This is a standard query without shortcuts. What is the value of associated with key 11? Message goes to 4 because 3 knows it doesn't have it. 4 knows it doesn't have it, sends it to 5, which knows it doesn't have it, sends it to 6, and so on until it gets to 12, and 12 realizes that it has it. It responds to 3, I've got it, and there we have 1, 2, 3, 4, 5, 6 messages. Now let's try it using shortcuts. What is the value of key 11? A message goes to 8. 8 sends the message to 12. 12 responds to 3, I have the value. We have reduced the messages from 6 to 3. Okay, this was a long one, so let's take a break here and sort through all the material we just now covered, and when you take care of any assignments you may have, and when you are finished, come on back and we will go to, what is it, 13 at this point?